Good morning. Are you ready to start Chapter 7? And we're going to look at Section 7.3 today, which is using the square root property to solve quadratic equations. The square root property, product property, reminds us that if we have the square root with two numbers underneath, or any root for that matter, in fact, this is called the radical. This is called the radical. The absence of a number here makes it the square root, but we could have any number. We could have a 3, any number at all. So we call that the radical sign. Whenever we have two numbers under the radical sign, it can be rewritten as separate numbers. So let's take a look at what that might look like. So as we scroll down here, just a moment, I want to remind you that I wrote on the whiteboard a while ago, but it's really important for you to know what a perfect square is. Remember that a perfect square is a number times itself, and it results in some very specific numbers that if we recognize them quickly, it will make us as mathematicians be much more efficient. So we already know that 2 squared is 4, and 3 squared is 9, 6 squared is 36, and so on. But even if you can recognize from 11 to 15, that will be very helpful, particularly in this assignment. So maybe spend a little time reminding yourself of what those might look like. Now let's simplify the radical square root of 20. The reason why we want to be able to recognize square numbers is because we want to say to ourselves, what is the largest square times another number that would equal 20? And if you look on this part of your screen, you can see that if we were to multiply 4 times 5, it would equal 20, and 4 is a perfect square. The reason why we want to find the perfect square is so that we can simplify the square root of 4 to be 2. We cannot simplify the square root of 5 any further, and that's fine. The key here is you want to leave your answer as 2 square root of 5 and not as 4.472135955, because that's an approximation. Now you can use your calculator to put in the square root of 20 and the 2 square root 5 to make sure that you simplified it correctly. So know that that is definitely a good tool to double check, but certainly not what I'm looking for in the answers, nor will the back of your book match that. So let's take a look now. We can simplify the square root of 32. The first thing we're asking ourselves is, what is the largest square number that we can think of that will multiply by another number to equal 32? You might first have thought 4 times 8, but there's actually a larger perfect square, 16. So if we rewrite 32 as 16 times 2, then we can rewrite that as the square root of 16 times the square root of 2. The square root of 16 is 4, and the square root of 2 cannot be simplified. So we have the answer 4 square root of 2. Now, using the product property to simplify square roots, we can then start to find answers to equations and other things, and that's where we're working towards. But one thing that we have to remember is that if we have the radical sign over an entire fraction, so this is including a over b, we can rewrite it as the square root of a over the square root of b. That will be very, very helpful here in just a moment. So make sure that you can rewrite those things. So let's take a look at simplifying the square root of 7/64. We can rewrite that as the square root of 7 over the square root of 64. The reason why that's helpful is because we can then simplify the square root of 64 to simply be the number 8, and we cannot simplify the square root of 7, so that is the answer. No more simplification can happen. Now, let's take a look at simplifying this 2 over the square root of 3. Mathematicians are a little quirky, and we do not want a radical sign in the denominator. So we must get rid of that sign in order for us to consider our solution as simple as possible. Recall here that if we were to multiply the square root of 3 times the square root of 3, that would be, we can rewrite it in reverse of what we've been doing and put both 3's under the radical sign, which gives us the square root of 9, and we all know that the answer is 3. So that is always your goal. Multiply the denominator by itself to get rid of the radical sign. So let's go over here. Now, we know that 2 over the square root of 3, we can multiply it by 1 and not change anything. The whole reason why they're showing you this is so that you know the reason why we can multiply the square root of 3 over the square root of 3, because technically that's equal to 1. So that doesn't change the value of the original fraction. So when we multiply this, we get 2 times the square root of 3, and we get square root of 3 times square root of 3, which is the square root of 9. Now, finally, when we get rid of that radical sign in the denominator, we have our final answer in the most simple form that we can get. Let's take a look at one more. Here we're looking at the square root of 5/18. We will rewrite that as the square root of 5 over the square root of 18. We're asking yourself, what is the largest square number that can be multiplied by something to equal 18? And that is 9 times 2. So we can simplify. They kind of skipped a step here. So this is really the square root of 9 and the square root of 2. That's how they got to this 3. They took the square root of 9. So we now have the square root of 5 over the square root of 5 over 3 times the square root of 2. Mathematicians won't allow you to leave the square root in the denominator, so we multiply by 1 in the form of square root of 2 over square root of 2. 5 times 2 is 10, and neither one of those can be simplified, so we go to the square root of 10. Now, 3 times the square root of 4. The square root of 4 is equal to 2, so we end up with 3 times 2 in the denominator, which is 6. So our most simplified answer is the square root of 10 over 6. Now, so let's think about what we've done in steps. To simplify a radical expression, first we use the quotient property of square root so that no radicand is in a fraction. So we rewrite it as the square root of something over the square root of something. We use the product property, so the square roots and radicands have perfect squares in them, so rewriting them with 4, 16, 25, 9, etc. When we say rationalize the denominator, we are talking about multiplying the denominator by itself if there's a square root, so that we get rid of any square roots in the denominator, and then we repeat until everything is simplified. Those are the steps for simplifying a radical expression. Now, let's remember what we've talked about in the past, which is if we're taking the square root of each side and the exponent is even, which square root will always be even because 2 is even, we have to remember that we do plus or minus on the opposite side. So x squared, if we were to take the square root of each side, because x squared is even, we know that we must do plus or negative the square root of k. So that's important to remember. Otherwise, you're going to miss 1/2 of your solution because it's going to have a positive and a negative answer. So looking here, if we were to find x squared is equal to 16, we know that x could be a positive 4 or a negative 4, because if we go backwards and we square 4, we know it's 16. But if we square a negative 4, it's also 16. So that's the same reason why when we find the square root of 45, we have plus or minus, and our answer is plus or minus 3 times the square root of 5. Now let's use the square root property to actually solve an equation. So we have 3x squared minus 5 equals 6. First and foremost, you have to get the squared term by itself. So we're going to add 5 to each side. We're going to divide by 3. Then we're going to take the square root. As soon as we take the square root, we add that plus or minus sign. Now this radical sign is over the entire fraction 11/3. So we rewrite it as the square root of 11 over the square root of 3 here. We cannot have the square root of 3 in the denominator, so we multiply both the numerator and the denominator by square root of 3. Because 11 and 3 cannot be simplified by themselves, we multiply them together and we get the 33. Square root of 3 times the square root of 3 is 3, and we don't lose the plus or minus throughout the entire process. So those would be ways to use the square root property to solve equations. Now, if you have a squared term inside of parentheses, that is isolated by itself. So now you take the square root of each side, and that gets rid of the parentheses and leaves you with 3w minus 4, again plus or minus the square root of 36. Now we're trying to find w, so we go, we simplify the square root of 36 to be 6, and we add 4 to each side. So one thing that we know is we are going to have two possible solutions now. So we have to operate two different ways going down. So when we add 4 to the negative 6, we get a negative 2, but when we add 4 to the positive 6, we get 10. So now we divide by 3. The two answers we get are negative 2/3 and a positive 10/3. So it is important that we remember that we have the plus or minus sign. Otherwise, we would have simply gotten only one of those solutions and not both of them. Looking at this problem, the quantity x plus 5 halves the quantity squared equals 31/4. We are going to take the square root of each side, and when we do so, we lose the parentheses on this side and we add the plus or minus on the right side. Now we rewrite the radicals so that they're each under a radical sign here, and we get the square root of 31 over the square root of 2. Now we are going to subtract 5 halves from the left-hand side and move it to the right. When we do so, we end up with this solution, negative 5 halves plus or minus the square root of 31 over 2. Because both of these have a common denominator, we can simplify our answer here. This will match the back of your book. I will be happy with anything like this on future tests. But mathematicians like it to be in the most simple form, so it would be best to put it under one denominator. Now, let's take a look at why we might want to find an x-intercept. Find the x-intercepts of a parabola. To find that, we know that the output is 0. The x-intercepts cross the x-axis, which means it goes up vertically, 0. So we're going to set this equation equal to 0. When we do so, we subtract 20 to both sides. We divide by a negative 2. Before, we need to be in this form before we can do the square root property. We have to have this side isolated as a squared term. So now we can take the square root of each side. We know that that's going to give us a plus or minus 10, square root of 10, and it gets rid of the parentheses on the other side. Now we add 7 to each side. Do not add the 7 under the radical. 7 is outside the radical because we really can't simplify 7 plus or minus square root of 10. That doesn't simplify. So it's key here, do not put that under the radical sign. The x-intercepts are 7 minus the square root of 10 and 0, that's 1 point, and 7 plus the square root of 10 and 0. So that is where it is crossing the x-axis. So finding the x-intercepts has us understanding that that is where it crosses, and we should be able to check that on our graphing calculator. So now what we've done is we've taken 7 plus the square root of 10. I have a lag here, sorry. Ooh, it's not working. Let me try this one more time. 7 plus the square root of 10. Yes, that's the square root of 10. Gives you an approximate decimal. That approximate decimal is going to be one of these 2 points where it's crossing the x-axis. So that allows you to double check your work and make sure that you found the correct values. So that's one way to double check things that you should be working on. The screen froze for me. Sorry, we're having an internet delay here using the software. So let's use our quadratic model to make predictions. When we're using it to make predictions, we will put these in list 1 and the years in list 1 of your graphing calculator and the number of vehicles, used vehicles, in list 2. So when you put those in, we will be able to use our linear regression and put up a scatter plot. So let's take a look at what that scatter plot might look like. So using the graphing calculator to draw your scatter plot, it should appear like this, and this allows us to decide, is it a parabola that's going to best match this? Sure is. We know it's not linear, and we also know that it is not exponential due to the shape of the graph. So we know that we want to use a quadratic regression. When we do that, we can use the quadratic regression simply to double check our work that we're going to do now. And you'll see why we want to learn to do solving the equation this way, because it helps us use the square root property in which we just learned. So if you remember, when we're solving for a quadratic model, we pick the lowest point that we were looking for here, which was 2, 4.2, and we choose another one up slightly, but that would make a good reference, 4, 5, 1. So those will be the 2 points that we use, also substituting those in the vertex form of a quadratic formula. So if you remember, we had the point 2, 4, 2, and 4, 5.1. So we are going to write those as reminders up here. And we are going to write 2, 4.2. It is not wanting to write today. Let me erase this and try one more time. We have a internet delay. Parenthesis, 2, comma, 4.2 is one of the points, and that can be found in just a moment. And then we have the point 4 and 5.1. So those would be the points that we are going to be using going forward. So we know that I believe the screen has a typo. This should be 2, which is why this is a 2 here. So the point 2 and 4.2 represent the vertex, so they're in these positions. X and Y represent 4 and 5.1, and that's why they are in those positions. Now you have 4 minus the 2 that I just corrected gives you 2 in the parentheses. So 2 squared is back to 4. So you have 5.1 equals 4a plus 4.2. Remember, we're trying to find a, so we divide by 4 on each side, and a is equal to 0.225. Now, you can substitute back into the vertex equation. Here we found our a. This is the x value of the vertex, and this is the y value of the vertex. And you can see that that's why they had a typo on their screen in step 1. They realized it should be 2 down here. So that is the equation that we're going to look for and use going forward. So let's model this and see what it looks like in our scatter plot screen. When we use this model for the scatter plot, you can see it lines up very nicely. So now let's take a moment to solve for what might this look like when we use 7.7 for f of t and then solve for t. That is, when will those cars be at 7.7 million cars? So this looks like the problems we did before. We subtract 4.2 from each side. We divide by the 0.225 to get our squared term by itself. We take the square root of each side, which leaves us a plus or minus, and it's kind of messy here. So we leave it messy for now, and we add 2 to each side. When we add 2 to each side, we know that we have the 2 plus or minus the square root of 3.5 divided by 0.225. Now, we divide that into both scenarios, the minus the radical and a plus the radical, and we get these approximations. And we get these approximations because it is of t years since 2010. So when t is equal to a negative 0.94, that's about 2 years before 2010, which would be 2008. And then we get 5.9, which is about 6 years after 2010. And that's how they get the 2016. So our model says that we'll have 7.7 million cars for sale that happened both in 2008 and 2016. Now, we're going to introduce the last little bit of this chapter, which is an imaginary unit. An imaginary unit is represented by the letter I. The square root of a negative 1 can be written as the letter I, which is an imaginary number, and it cannot be found on the typical number line. So, we always want as mathematicians to have a positive number under the radical sign, so whenever you have a negative number, you simply use the letter I to bring it to the front and outside and leave the positive number under the radical. So, for example, a square root of 49 is the negative square root of 49 can be rewritten as taking the I out and rewriting it as a square root of 49. That is 7i. Negative square root of negative 24, we don't do anything with the negative sign on the outside, but however, to get the negative 24 to positive, we rewrite it as a negative I square root of 24. Now, we know that 24 can be simplified to 4 times 6. The square root of 4 is 2. So now we end up with a negative 2i square root of 6 being our most simple answer. So we can also use complex numbers, and complex numbers are where a plus bi, where a and b are the real numbers, but that I is the negative square root, which makes it imaginary. Now you might be wondering why we want to study this, and it comes into play for this idea of the quadratic. With the quadratic, if these were our axes, we could have a quadratic that comes down and touches the x-axis in 2 unique spots like this. We could also have a quadratic that comes down and touches the axis in 1 exact spot. And lastly, we could have a quadratic that doesn't touch the x-axis at all. If it's this scenario, you will have answers that have complex numbers. So that's the reason why they're introducing that at this time. So let's take a look down here at this example. At this example, we do what we've always done. Take the square root of each side, plus or minus is the answer, but now we have a negative 28 under the radical. So we bring out the I. We simplify the square root of 28 to be 2 square root of 7, because we know that 4 times 7 equals 28. And then last, to get x by itself, we subtract 3. This means that this parabola will not touch the x-axis. I hope you continue to have a great week, and this is helpful in you doing your homework for 7.3.